Section 8.6, Parametric Equations. So, way back in Lesson 1-4, at the very beginning of the year, you learned how to write the equation of a line in the coordinate plane. For objects that are moving in a straight line, there is a more useful way of writing equations for the line described by the object's path using vectors. If a line passes through the points P and Q, P1 and P2 and is parallel to the vector A, the vector P1, P2 is also parallel to vector A. So vector P1, P2 must be a scalar multiple of A. We can use t as our scalar, and we can write the equation of vector P1, P2 as t times vector A. So both sides of the equation are vectors. So this is the vector equation of the line. Since A is parallel to the line, that's the direction vector, and scalar t is called the parameter. All right, so a line through some point P1 parallel to the vector A is defined as defined by the set of points P1 and P2 such that vector P1, P2 equals t times A for some real number t. What that means is that you have the 2 points, you get the vector from those 2 points, and set that equal to t times vector A. So, a vector equation describing a line passing through point 1, 4 and parallel to A for -2. We would also need some point P2, and we'll just call those points x and y. So the vector, we subtract the x components, x minus 1. We subtract the y components, y minus 4. And we set that equal to t times 3, -2. So x minus 1, y minus 4 is equal to t times 3, -2. That's the vector equation of the line. So you can write the vector equation as 2 equations relating to the horizontal and vertical components of these 2 vectors separately, right? So if we were to, when we multiply a vector by a scalar, we multiply both components, or all components of the vector, by that scalar. So we could make this 3t -2. And then we can set the x components equal to each other and the y components equal to each other. So that gives you then 2 equations, x equals x1 plus ta1 and y equals y1 plus ta2. So if we have the parametric equation for a line parallel to Q, 6, -3, and passing through a point, -2, -4, right? We have some other point, x, y. So our equation is going to be, our first vector is going to be x plus 2, and our second one is going to be y plus 4. And we're going to set that equal to t times the parallel vector 6, -3. And so we can make that 6t -3t equal to x plus 2, y plus 4. And then set the x components equal to each other. So x plus 2 equals 6t, or x equals 6t minus 2. And then y plus 4 equals -3t, which would be y equals -3t minus 4. So if we make a table of values, we pick numbers for t, and we plug them in for x and y. So if I pick t equal to, say, 0, then my x is going to be -2 and my y is going to be -4. If I pick t equal to 1, 6 times 1 is 6, minus 2 is 4. -3 times 1 would be -3, minus 4 would be -7. And I could pick t equal to 2. If I pick t equal to 2, 6 times 2 would be 12, minus 2 would be 10. -3 times 2 would be -6, minus 4 would be -10. So I've got a point at 10, -10. I've got a point at 4, -7. And I've got a point at -2, -4. And so that gives me enough points that I can draw a line through them. Okay, so write parametric equations of y equals -4x plus 7. So we want to split this into two equations, and we want to have x and y be in terms of t instead. So one very easy way to do this would be to make x equal to t, and then y would be -4t plus 7. All right, if x is equal to t, then y would be -4t plus 7. Parametric equations for the line. There are potentially other ways that you could do this. Like you could make x equal to 2t, and then y would be x equal to 2t, and then y would be -8t plus 7. But this would be the easiest way to do it. Air racing's origins date back to the early 1900s when aviation began. One of the most important races is the National Championship Air Race held every year in Reno, Nevada. In the competition, supposed pilot Bob Hanna passes the starting gate at a speed of 410.7 miles per hour. 15 seconds later, Dennis Sanders flies by at 412.9 miles per hour. They're racing for the next 500 miles. Assume that both planes maintain a constant speed. How long is it until the second plane overtakes the first? And how far have both planes traveled when the second plane overtakes the first? So we want the parametric equations of these two, their distance in terms of time. So the first plane is traveling at a speed of 410.7 miles per hour. And so 15 seconds later, the other one is going at 412.9 miles per hour. So the first plane is traveling at 410.7 miles per hour times t. So the distance that plane 1 travels is going to be 410.7 times t. Right? Where x is the distance that it travels. T is in hours. The second plane is traveling at 412.9 miles per hour, but the time is a little bit less, right? We're going from where it passes the starting gate, right? So Dennis Sanders, the second plane, passes the starting gate 15 seconds later. So the time, we need to subtract 15 seconds. But remember that our time is in hours because our speed is in miles per hour. So we need to convert 15 seconds into hours. So 15 seconds, do your dimensional analysis, right? 60 seconds in 1 minute, 60, that should have been in the denominator, 60 minutes in 1 hour. Your seconds cancel out, your minutes cancel out, and you're going to get an answer in hours. So if you do 15 divided by 3600, you're going to get 0.0042. So t minus 0.0042 hours. It's technically x2, right? So that's the distance. This is the distance, the equation for the distance that the first plane travels in terms of time t. And this is the distance the second plane travels in terms of time t. So how long is it until the second plane overtakes the first? When the second plane overtakes the first, there's going to be a brief amount of time where they're exactly the same distance away from the starting line. So what we want to do is we want to set x1 and x2 equal to each other. So 410.7t equals 412.9 t minus 0.0042. We want to distribute this 412.9. So this is 412.9 t minus 0.0042 times 412.9. 0.042 times 412.9. Which would be 1.73. And then set that equal to 410.7t. Move all of our t's over to one side. And that's going to give us negative 2.2t equals negative 1.73 divided by negative 2.2. And we're going to get that t equals 1.73 over 2.2, which is 0.7879 seconds. Hours. Our t was in terms of hours, which makes a lot more sense. All right, so 0.79 hours. How far will both planes have traveled when the second plane overtakes the first? We can then take this t and plug it back into either one of these equations. I'm going to plug it back into the first one just to make things a little bit easier. So the distance is going to be 410.7 times 0.79, which is 324.5 miles. Write an equation in slope-intercept form of the line whose parametric equations are x equals negative 5 plus 4t and y equals 2 minus 3t. So in slope-intercept form, we want y equals mx plus b. What we're going to do is we're going to take this first equation here, we're going to solve this for t, and then we can plug that in here. So if x equals negative 5 plus 4t, we're going to add 5 to both sides. X plus 5 equals 4t, and we're going to divide by 4. So we get that t equals x over 4 plus 5/4. Now we're going to take that, and we're going to plug that into y. So we get y equals 2 minus 3x over 4 plus 5 over 4. So 2 minus 3/4 x plus, minus, distribute the negative. All right, negative 3, so this becomes a minus 15/4. And then we want to combine our like terms here. 2 is equal to 8 over 4, so put the negative 3/4 x here. 8 over 4 minus 15 over 4 is going to be negative 7 over 4. And there's the equation of our line in slope-intercept form. And that's it for 8.6. Wasn't that fun?